Good morning, students. Myself, Vijay Shankar from ECE Department, Spherical Engineering College. Today, we are going to discuss about one of the important topic, the energy and potential. In the same unit of electrostatics. So, the energy and the potential. In this, the work done, the electric field intensity is defined as the force on unit test charge. We already know the electric field intensity E is equal to force per unit charge F by Q. That is nothing but Q by 4 pi epsilon naught R square into AR at the point charge, the formula of the electric field intensity. And now if I am taking the vector E bar is equal to electric field intensity is defined as the force on a unit test charge at that point at which we want to find the value of E bar. Consider an electric field due to the positive charge Q. If a unit test positive charge Q1 is placed at any point in this field, let us take the charge Q is here in a space. Let us take this a space. The charge, the test charge QT. Let us take. If a unit test positive charge Q2 is placed at any point in the field, and here already there is a charge Q is there. Consider an electric field due to the positive charge Q. If a unit test charge Qt is placed at any point in this field, it experiences a repulsion force. And tends to move in the direction of the force. See, already the positive charge is already there, and we bring that test charge Q nearer by that. There is a repulsion because both are the positive charges. Repulsion occurs due to the positive charge in the space and tends to move in the direction of the forces. But if the positive test charge Qt is moved towards the positive base charge Q, then it is required to be moved against the electric field of the charge Q. That is, against the repulsion force exerted by the charge Q on the test charge Qt. While doing so, the external source has to do work to be move the test charge Qt against the electric field. This movement of charge requires to expand the energy. This work done becomes a potential energy of the test charge Qt at the point at which it is moved. See, clearly I will explain once again. The work is said to be done when the test charge is moved against the electric field. Let us take here the electric field direction is, let us assume, in the right hand side. Now, there is a Q here. Now I am taking the test charge Qt, move this Qt against the direction of the electric field. Against the direction of the electric field, already there is a positive charge, and now we can move this Qt nearer by. There is a repulsion occurs. The work done is said to be done. Work is said to be done when the test charge is moved against the electric field. So electric field is in this direction. We can move the test charges against the direction, opposite direction towards. Thereby, a work is done, or work is said to be done when the test charge is moved towards the opposite side of the electric field intensity. Got it, my friends? I clearly see here. Consider a positive charge Q1. Consider a positive charge Q1 and its electric field E bar. Electric field E bar. If a positive test charge Q1 is placed in this field, it will move due to the force of repulsion. If a positive test charge Q2 is placed in this field, it will move due to the force of repulsion. Due to the force of the Q1, the Q2 is moved opposite direction. Let the moment of charge Q2 is DL. The direction in which the movement has taken place is denoted by the unit vector AL bar in the direction of DL. It is a direction, it is a AL bar, that is a force F test charge. According to the Coulomb's law, the force exerted by the field E bar is given by, according to the Coulomb's law, the force exerted by the field E bar is given by the F is equal to Q into E. Actually, it is a electric field E bar is equal to F bar by the Q. Now the F bar is equal to Q into E bar. Okay, F is nothing but in the terms of force newtons. But the component of this force exerted by the field in the direction of DL is responsible to move the charge Q2 through the distance DL. Now, so the Ft bar is equal to, because it is in the direction of AL bar, the vector, the test charge force Ft bar is equal to the magnitude F bar dot AL, because it is in the unit vector shows the AL bar direction to the distance of DL. What is the F bar? We already got the Q into E bar. Q into E bar dot AL bar. Okay, now that force on the first test charge is Q into E bar dot AL bar. Okay. Now the applied force is opposite to the electric field direction. Means the charge Q is already there. There is a Q1. And now I am taking that is a test charge Q3 is moved opposite direction to the electric field intensity E bar. The applied force is opposite direction. So applied force is equal to, because it is a repulsion. Repulsion takes place, applied force is equal to the test charge force, the Ft bar, it is a minus indication. So when I am moving here, actually the opposite is the direction, the repulsion occurs due to the charge Q1. That is a minus. So the minus Ft bar means the Qt that is a Qt into E bar dot DL, AL bar dot AL bar. Applied force is equal to the minus the value here, that is equal to minus Qt into E bar dot AL bar. It is the work is said to be done. Thus, there is expenditure of energy which is given by the product of force and the distance. Mathematically, the differential work done by an external source. So here mathematically the differential work done by an external source in moving the charge Q2 through a distance dl against the direction of the electric field is given by, that is a work done, the dW is equal to the differential work done is equal to applied force the cross product of the dl, the opposite direction. Okay, my dear students, that is equal to, what is the applied force? Minus qt into E bar dot al bar, and cross product of dl bar, cross product of the dl bar, or it is a dl, not the dl bar actually, my dear students, dl. We know whenever if we can take the dl is equal to dl is equal to dl, it's the same thing. When I'm using the vector product, the dl is a magnitude and it having the al bar direction, showing that when the magnitude is a dl is equal to dl means when it shows the vector, it having the direction also, it is a direction towards the al bar. So now I'm taking it is a distance vector dl bar is equal to q into qt into e bar. So these two is a product only, my dear students, it's a into. So dot dl into al bar, dl into al bar. So dl into al bar is nothing but the dl bar. So change of the differential work done is equal to qt into e bar dot dl bar, dot dl bar. Okay. It is a work done is something but the units is joules. Okay, my dear students. Thus, the charge Q is moved from the initial position to the final position against the direction of electric field, that the total work done is obtained. Okay, the charge Q1 is already there, and the test vector, if I am taking the initial value to the final value of 2, you can move this against the direction of the electric field. The test charge is moved against the direction of the electric field from initial value to the final value, because it is also positive charge and it is also the positive charge. But forcefully we are moving the QT towards the Q1 against the opposite direction of the electric field from initial point to the final point. Actually, it is a repulsion occurs. Forcefully we are moving. Thus, if a charge is moved from the initial position to the final position against the direction of electric field E bar, then the total work done is obtained. Here there is a total work done is obtained by integrating the differential work done over the distance from initial position to the final position. See the dW, apply the integral here, you get the W is equal to integral of initial value to the final value dW. So what is the dW? We got initial value to the final value. dW is a minus Q E bar dot dl. Minus Q E bar dot dl. So then the W by Q, let us take it is a W is equal to, first you can write the W is equal to minus Q integral initial value to the final value E bar dot dl. E bar dot dl. Okay, the work done in measured in the joules. The work done W is equal to minus Q integral initial value to the final value E bar dot dl bar. Okay, but let that initial value is B. The work done W is equal to minus Q into integral B to A E bar dot dl. E bar dot dl. Okay. Now the line integral, consider the charge is moved from initial position point position B to the final position A against the electric field when the work done is given by the work is W is equal to minus B to A E bar dot dl. This is called the line integral, where E bar dot dl bar gives the component of E bar along the direction of dl bar. Okay. This is a formula for the work done minus. Now something here, there is a different DL1, DL2, DL3, DL4 and DL5 is there. W is equal to minus Q E bar dot the different points where we have to take the test charge and we have to move against the direction of the electric field, the total charge, total differential lengths, the DL bar plus the DL2 bar plus up to so on the DL5 bar, I think, and so on. So forget about this, is not the somewhat important. The differential length of the vector, the DL bar, is for Cartesian coordinate system, cylindrical coordinate system, and the spherical coordinate system. Already we know the DL bar is equal to dx ax, dy ay, and dz dz. And cylindrical coordinate system, DL bar is equal to dr ar bar plus r into d phi a phi bar and dz into az bar. And for the spherical coordinate system, DL bar is equal to dr ar bar plus r d theta a theta bar plus r sine theta d phi a phi bar. Okay. So next one, you can see the potential difference. We got the work done is equal to minus Q the integral B to A E bar dot dl bar. The work done. The work done in moving a point charge Q from a point B to A, the electric field intensity in the electric field E bar is given by the work is equal to minus Q the integral B to A E bar dot dl bar. Now the potential charge is not the potential charge, potential difference. If a charge Q is selected as a unit test charge, then from the above equation, we get the work done in moving the unit charge from B to A in the electric field E bar. This work done in moving the unit charge from point B to A in the field E bar is called the potential difference between the points. Simply we can say work done per unit charge in moving charge from work done per unit charge in moving unit charge from B to A in the electric field is called potential difference. This is a definition, my dear students, for the potential difference. Work done per unit charge is called the potential B. the work done per unit charge in moving the unit charge from B to A in the electric field E bar is called the potential difference. So work done per unit charge is equal to, now it becomes of integral B to A E bar dot DL bar. Okay. What is that? Work done per unit charge is nothing but the potential difference. Potential difference E to B, because it starts from the B and then to the A, is equal to minus integral B to A E bar dot DL bar. E bar dot DL bar. The potential difference B is equal. Got it, my students? And 1 volt is a 1 joule per coulomb. So joules in the work done, and the Q is a coulomb. So the volts, or otherwise it is a coulomb per, or the coulomb joules per coulomb. Unit charge. The potential difference is a work done per unit charge. Okay. Now, the potential due to the point charge. Potential due to the point charge. See, there is a charge Q is already there from the positive charge. There is a magnetic, not the magnetic, electric flux lines is terminated radially, generated radially and terminated towards infinite or terminating towards the negative charge. In this space, consider a point charge located at the origin of spherical coordinate system producing E bar radially in all the directions as shown in the figure. Assume a free space, the electric field due to a point charge Q at a point having the radial distance R from the origin is given by the formula we already know. E is equal to Q by 4 pi epsilon naught R square into AR bar. Consider a unit charge which is placed at a point P. Let us take here at point P. The unit charge QT, let us take, which is placed at a point P, which is a radial distance of R from the origin, or it is RP. So because it is a P term, P distance is there, RP. From the origin, it is moved against the direction of E bar. So the direction of E bar is radially here. You can move this charge against the direction of E bar from point B to the point A. From point B to the point A. The point A is the distance from origin is RA, and point B, the distance from origin is R. Point A is its radial distance of RA from the origin. The differential length of spherical coordinate system, we already know that dr is one of the differential element, and r d theta is another differential element, and r sin theta d phi is another differential element. So you can add all these terms in the direction of AR and A theta bar and the A phi bar. It's a differential like the DL is equal to dr AR bar plus R into d theta A theta bar plus R sin theta d phi and A phi bar. So the potential difference VAB between the points A and B is given by, the formula is there, VAB is equal to minus integral B to A E bar dot DL bar. B is RB, the distance from origin, and A is the point from the origin to the A is RA distance. So you can keep the B as RB and A is RA. The E bar is equal to Q by 4 pi epsilon naught R square into AR bar dot the differential length, all the terms. So AR and AR only having the 1, the remaining is zeros. So Q by 4 pi epsilon naught R square into dr. These are two magnitudes of electric field and the differential length. So Q by 4 pi epsilon naught is a constant, and 1 by R square into dr is nothing but minus 1 by R. the integral of 1 by r square is minus 1 by r with upper limit is rb, not the rb, ra, and lower limit is r. Okay, my dear students. So q by 4 pi epsilon naught into, to take the minus here, the minus q by 4 pi epsilon naught into 1 by r. Upper limit is 1 by ra minus 1 by rb. VAB is equal to. Okay, my dear students. And now to bring that is a minus, multiply the minus with the two terms, 1 by RA minus 1 by RB. The voltage VAB is equal to, the voltage VAB is equal to Q by 4 pi epsilon naught, Q by 4 pi epsilon naught. After multiplying the minus here, 1 by RA minus 1 by RB. 1 by RA minus 1 by RB. The voltage or the potential due to the point charge Q by 4 pi epsilon naught 1 by RA minus 1 by RB. So when RB is greater than RA, RB is greater than RA, 1 by RB is less than the 1 by RA, and VAB is positive always. This indicates the work done by external source by moving the unit charge from point B to A. So because the distance is B is very much greater than, not very much, it's greater than, RB is greater than RA. But definitely the inverse is less than only 1 by RB less than the 1 by RA. So finally the voltage V is equal to, simply we can write as Q by 4 pi epsilon naught is a positive always. 1 by RA is 1 by RB is a less than compared to the 1 by RA. Definitely this voltage is always a positive. VAB is a positive. Got it, my dear students? And this is a 1 by RA minus 1 by RB. Or you can write as RB minus RA by RA into RB. So potential due to the point charge. In the concept of the absolute potential, here you can see, instead of the potential difference, it is a more convenient to express the absolute potential of various points in the field. Such absolute potential are measured with respect of specified reference position, such as the reference position is assumed to be the zero potential. See here, consider the potential difference VAB to the moment of unit charge from B to A in a field of point charge Q is given by, we already derived this expression. See, for this, we can take here a shielded cable. The conductor is shielded as shown in the figure. The outer shield is grounded. See, the outer shield is grounded to the minimize of the interference of electrical external signals with the signal carried by the inner conductor. In such case, the outer shield is taken as a reference with respect to which the potential of various points are defined. Similarly, in a cathode ray tube, the metallic shield around the tube is taken as a zero potential reference with respect to the reference potential of various points are measured. Now see here, we know the potential difference due to the moment of unit charge from B to A in the field of charge Q is given that is a VAB is equal to Q by 4 pi epsilon naught 1 by RA minus 1 by RB. Got it, my dear students? Now let us, the charge is moved from infinite. Charge is moved from the infinite to the point A. Means I take the charge Q1 and there is a direction of the radially, the direction of the E bar. So it is taken at the origin and the distance of A point from origin is RA. Now I am taking the B is infinite. Okay. The charge is moved from infinite to the point A, that is RB tends to infinite. 1 by RB is a 0. When the B point is taken from the infinite, 1 by RB is the 0 value. We have only the BAB is equal to Q by 4 pi epsilon naught into 1 by RA minus 1 by infinite, because RB is the distance from origin is infinite. It becomes a 0, it having only the Q by 4 pi epsilon naught RA, and this is becomes of VA only. The VA is equal to Q by 4 pi epsilon naught RA, and VB is equal to Q by 4 pi epsilon naught RB. Now the voltage difference, you can take the V is equal to, the potential V is equal to VA minus VB. What is the VA? We have the Q by 4 pi epsilon naught RA minus Q by 4 pi epsilon naught RB. Now the common term is there here, the Q by 4 pi epsilon naught into 1 by RA minus 1 by RB, the same thing. So the voltage at the point V, point A is VA is equal to Q by 4 pi epsilon naught RA, at the point B is a Q by 4 pi epsilon naught RB. The absolute potential. So now the VAB is equal to VA minus VB. Potential difference can be expressed as a difference between the absolute potentials of the 2 points. The absolute potential at any point in the electric field is defined as work done in the moving the unit charge from infinite to the point A against the direction of the field, has the potential at any point which is at a distance of R from the origin of a spherical system where the point charge is located. B is equal to Q by 4 pi epsilon naught R. I'm not taking the A or the B. It's simple from the origin. Any point at which is at the distance R from the origin of a spherical system where the point charge Q is located. This reference point is at the infinite. B is equal to Q by 4 pi epsilon naught R. But it demonstrates. C means the Q by 4 pi epsilon naught is a constant here. B is always a inversely proportional to the distance from the origin, the point, any point with a distance from the origin. Okay. If the point is not from the origin, what is the potential difference? Or the potential, not the potential difference, the potential due to the point charge not at the origin. Not at the origin means from here the origin is there, the point A, and the charge Q is here. Here the R is a distance and it is a R dash is a distance. So VA is equal to Q by 4 pi epsilon naught R minus R dash is the distance of Q to A, which is not at the origin. The RA is equal to R minus R dash. RA is equal to R minus R dash. If it is many points are there, let us take the point potential due to the several point charges. VA1 is equal to Q by 4 pi epsilon naught R1. VA2 is Q2 by 4 pi epsilon naught R2. The charge Q1, the charge Q2, that's the charge Q3, and so on. The charge Q1 from the origin is R1, we can consider. Charge Q2, that is R2. and charge Q3 is R3, and charge Qn is the distance is Rn. But from the origin to the point A is R. From the origin to the point A is R. But the different charges we have, the distance is R1, R2, and so on. So the potential is the potential due to the several point charges we have. Only one charge, 1 point charge is there, means Q by 4 pi epsilon naught R only. And we have the different point charges, several point charges are there. Let us the charge Q1 by the 4 pi epsilon naught R. R1 is R minus R, small letters of R minus R, the distance. If we voltage here, the potential is V2, the Q2 is a charge, and 4 pi epsilon naught R minus R. That is nothing but R2, capital R. The total R minus R2, R minus R3, and so on, R minus Rn. So VA is equal to the sum of M is equal to 1 to N, the QM. M is, when M is equal to 1, Q1 by 4 pi epsilon naught R minus R1. When M is equal to 2, Q2 by 4 pi epsilon naught R minus R2, and so on. Okay, my dear students. The potential due to the several point charges, V is equal